Okay, so let's start. So today again, a different technique to design parameterized algorithms, and this will be the last technique that you'll be seeing in the summer school. So this technique is called color coding. Okay. And again, this technique is used to design FPT algorithms, fixed parameter tractable algorithms. And we'll see the illustration of this technique using an example problem. And the problem that we'll be looking today is not vertex cover for a change. Decision version of the Hamiltonian path problem. So what's that? You're given as input a graph G and an integer K. And the algorithm outputs yes if graph has a path of length at least k, a simple path on at least k vertices. So if k is n, you're looking for a simple path on at least n vertices. So that's the Hamiltonian path problem, right? So in that way, it's a decision version of the Hamiltonian path problem. So again, we're solving the decision problem today again. So it outputs yes if there exists a simple path on k vertices, and it outputs no otherwise if there is no simple path on k vertices. Okay, so the problem is clear. So let us try to see. We have till now seen three techniques to prove that certain problems are FPT. That means they admit algorithms which have running time of the form. So we want to solve this problem in running time, which is some function of k, any function of k, I don't care, into some polynomial in n. N is the number of the vertices in the graph. Okay. So far we had seen kernelization to design such algorithms. We had seen branching to design such algorithms, and we had seen, yesterday we saw iterative compression. So before even going to color coding, let us see if we can do something about this problem using one of the techniques that we have already studied. So let's start with kernelization. So for kernelization, one can actually prove this problem does not admit a kernel of any size. When I say kernel of any size, remember kernel was, what was a kernel? You started with an instance and you came up with an equivalent instance in polynomial time whose size was bounded by some function of k. For vertex cover, for example, we showed a k square size kernel, and in the later class using LP, we gave a 2k size kernel. So for this problem, one can prove, again, this is beyond the scope of the summer school, but one can prove that unless something happens, which people don't believe to happen, like people don't believe that P is equal to NP. Similarly, there are some other set of conjectures which people don't believe. Unless those happen, this problem cannot have any kernel. Okay, sorry. Okay, this is not correct. This problem cannot have any polynomial kernel. That means this problem cannot have a kernel whose size is a polynomial function in k. But yes, one could design an exponential kernel for k. That's one thing that one could do to solve this problem. We'll not be looking at that today. Let's say branching. Can we do branching to solve this problem? That's not a right question. Can we or can we not? Do you see a naive or do you see a natural branching algorithm to solve this problem? Like usually the kind of branching that we have seen so far, what was the idea behind it? We branched we knew we were trying to find a set of vertices whose deletion makes the graph look like something. And to do branching, we were always trying to find a structure in the graph from where we knew that the solution has to pick at least one of the vertices from that structure. In the vertex cover, that structure was a single edge. So we know any solution has to pick one of the endpoints of that edge. In the case of triangle hitting set, we just quickly said yesterday that any solution has to pick one of the endpoints of this triangle. So one could branch. Here, at least at the first go, we don't see any structure on which we can branch, right? The question is there a path of length k in the graph, right? So it's not like a branching, at least a natural branching algorithm is not very clear in this case. So again, let's talk about iterative compression. In the iterative compression, again, the beauty of the iterative compression was that one could it was enough for some problems. It was enough to solve the compression problem. So if you're doing iterative compression, you should be able to solve the compression version of this problem. Now again, it's not clear how the compression version of this problem will look like. So in the compression problem, we say that we're always given a solution of size k plus 1. So what does it mean here? Does it mean that we're given a path of size k plus 1? If we're given a path of size k plus 1, we're anyways done. If you have a path of size k plus 1, you also have a path of size k, right? So one could say, okay, then maybe is it true that one is given a path of size k minus 1 and from there you want to get a path of size k? But again, for a compression problem, even if I give you a path of size k minus 1, see, we said we try to solve compression problem because in the compression problem we're already given a solution, and when we delete a solution, the resulting graph has some structure. So when we remove a vertex cover of the graph, the resulting graph had isolated vertices. When we removed the solution for the triangle hitting set, the resulting graph had no triangles. So when we designed an algorithm for the compression problem, we actually use the properties of this resulting graph, the nice structure of the resulting graph. But here again, even if I give you a set of vertices, say k minus 1 vertices which form a path, even if I delete them, the resulting graph could still be arbitrary, right? It doesn't impose any structure on the resulting graph. So, and hence again, we don't get any more insights on how we would go about doing some sort of iterative compression, at least for this problem. Like, again, this is all very intuitive. So at least intuitively, we don't see any natural strategies, like amongst the strategies that we've discussed so far for designing FPT algorithms, we don't see any strategy that is natural to attack this problem, at least intuitively. So hence, there is this new technique that we are looking at today, which is called color coding, to get an algorithm for this problem, to get an algorithm of this form, f of k into poly n. So what is the crux of this technique? Again, like in iterative compression, we said in order to solve the problem, for many problems, it's enough to solve the compression version of this problem. So if, for example, if I had to solve vertex cover, instead of solving vertex cover, if I solve the compression version of this problem, where I'm also given a solution of size k plus 1, if I have an algorithm to solve this problem, then using this algorithm, I can solve the actual vertex cover problem. So if this algorithm takes some f of k into polynomial in n time, the original problem can be solved into this much time into some linear function in n, right? This was the goal. So again, for color coding also, what we do is, we'll first see, instead of solving this problem, we'll solve a slightly different problem, which I'll define, which is basically the colorful version of this problem. I'll define what that is. For example, in iterative compression, we solve the compression version of that problem. Here, we'll solve a colorful version of that problem. I'll come to what it is. And we'll see that once we have an algorithm to solve a colorful version of this problem, an algorithm running in time some f of k into polynomial in n, then we can actually solve the original problem in this kind of a time, some g of k, maybe not the same function f of k that is there in the running time of the colorful version of the problem, but some g of k, which is again some function of k. I mean, we'll see what these are. Doubts? Let me begin by defining a colorful version of this problem. So, okay, this problem is called the k-path problem. So, I am now defining what is the colorful k-path problem. In the colorful k-path problem, again, in the input we are given a graph G and an integer k and a coloring of the vertices of the graph using k colors. So, think of the input graph as being colored with some k colors. Now, this coloring is not a proper coloring of the graph. So, the coloring that I give you might not be proper in the sense that it might be the case that there are two edges that get the same color. So, the way we should understand coloring is like there was a graph and I just painted every vertex of the graph with some color from 1 to k. So, assume that the colors are numbers. So, when I say a vertex get colored, some color as in a vertex either get colored 1, 2, 3, 4 or k. Okay. So, the vertices of the graph are just painted with some colors. So, this is the input that we get, a colored graph. Okay. So, formally what is a colored graph? It's a graph G together with a coloring function C. So, what is this coloring function? It takes a vertex of G and assigns it some color from 1 to k. So this is a graph which has been colored using k colors. This is the input of the problem for this problem. And now, what is the output? So in the original problem, we were interested in finding, is there a simple path on k vertices? In the colorful problem, we'll be interested, is there a simple path on k vertices which is colorful? When I say colorful, meaning I'm interested in finding a path on k vertices where all the vertices have different colors. So the original graph is colored. So when I find a path in the graph, that will be a colored path, right? So I'm not interested in finding any colored path of length k. I'm only interested in finding a path of length k where all the vertices get distinct colors. So the graph was colored with k vertices. So if there is a k path, I want that all the colors are used by this path and they are all used exactly once in this path. So what is the output? It outputs yes if there exists a colorful path in G. Okay, so let's see an example. Let's say this was the graph G, and let's say the vertices of the graph were colored with some 3 colors. Suppose k was 3 and the vertices of the graph were colored with 3 colors. So let's say this vertex was colored red. In the input, so the input graph suppose looked like this. Okay, and let's say the edges of the graph were of the form. So let's say this was the graph G and in the input, and k was 2 and this was the coloring that I had done to the graph. So this was my input graph, and in this input graph okay, let's say k was 3, and in this input graph I'm interested in finding a path on 3 vertices such that all its vertices are colored differently. Okay, so what is one such path? Yeah, so if you look at this path from here to here to here to here, this is a path on 3 vertices and all the vertices in this path are colored with different colors, right? So for example, if you'll see this, if this and this, so basically this is also a 3 length path, but I can't output this because there are 2 vertices colored red in this path. So there is only one solution in this graph, which is this red, green and blue path. Okay, so is the problem clear? I'll give you such a graph as input and you have to find me a colorful path in this graph of length k. So first what we'll see is, we'll see an algorithm to solve the colorful k path problem. And then we'll see that, okay, why is it enough to solve the colorful k-path problem in order to solve the original problem? Let's solve the colorful k-path problem. So what we're trying to do now is we're trying to solve the colorful k-path problem. So let's see. So what is the input? The input is a colored graph. It has been colored with k vertices. Let us look at let this be the collection of all vertices in the input graph that I've got colored 1. Let this be the collection of all vertices in the input graph that I've got colored 2. So on. These have got colored k. Okay, so basically these are the vertices which have got, these are the vertices which have got colored 1. Let's say 1 is color red. These are the next set is the vertices that have got colored 2. So 2 is green and so on. I mean, you'll use k colors. Suppose the kth color is blue. Okay, so this is how my input looks like. There are edges in the input graph. They could be anywhere. There could be edges even inside one color class. Because what I gave you was not a proper coloring. Okay, so this is how the input looks like, and we are interested, is there a path of length k that uses exactly one vertex from each color class? That's the question, right? So again, this is the input and the goal is to see, is there a path that uses exactly one vertex from each color class? Okay, and we want to solve this problem, and the kind of running time that we are allowed is f of k into poly n. See, I keep on writing this f of k. What is f of k? It is any function of k, okay? And when I write f of k, I write it in terms of f of k just to convey that when you're designing an algorithm, I have allowed you time that is like the time in terms of k could be as bad as you want. So if you're designing an algorithm, if you see some k things anywhere, you can do whatever you want to do with those k things, because like you can look at all possible subsets of it, you can look at all possible partitions of it, because all these numbers, all possible subsets of k are only 2 per k. So the kind of running time that I'll incur if I'm looking at all possible subsets will only be 2 per k, and f of k allows that. Now even after I've looked at all possible subsets of 2 per k, I can look at all possible, say, partitions of k, that will be some k per k. So 2 per k into k per k will again be some function of k, right? So when I write f of k, that's why I'm writing f of k, so that you can do whatever you want. You can play with k as you want to. There are no restrictions on how you can play with k. So here again, you have k and you can play with k the way you want to. When I say play with k, your algorithm can brute force in whatever way it wants to with k, because I don't care what is the dependence on k in the running time. It's some f of k, I don't care what this f of k is as of now. So again, can someone suggest an algorithm? For this problem, you have to find a path that uses exactly one colored vertex. What is it? We are looking for a path that uses one vertex of red, one vertex of blue, one vertex of every color, right? So as he says, you have a path in your mind. The path has to use one of these colors. Let us guess in what order will the colors appear on this path. So it's a colorful path. It has to use red. It has, like for example, suppose there were only 3 colors. So it has to use the red color, it has to use the green color, and it has to use the blue color, right? So a path in the graph could be of the form like the first vertex is red, the second vertex is green, the third vertex is blue, or maybe the first vertex is green in the path, the second vertex is red in the path, the third vertex is blue in the path. These are the only kind of colorful paths that you can have, right? So basically, look at all possible permutations of these colors. Like for these 3 colors, permutations will be red, green, blue, red, blue, green, green, red, blue, green, blue, red, and so on. So there are like 3 factorial. If there are 3 colors, there are 3 factorial possible orderings of these colors. Okay, so you just guess. So if there was a colorful k path, the colorful k path will visit these colors in some particular ordering. You just guess that ordering. When I say guess that ordering, as in you try to find a colorful path for every such ordering. So if once you have guessed an ordering, suppose I guess that the path that I'm looking for, will have first vertex will be green vertex in that path. Suppose I guess that, and let's say I guess that the second vertex will be red in that path, and the third vertex will be blue in that path. Suppose I guess that. Now, once I've guessed that, I know that my path. Once I guess that, what is the problem we are looking at? We are looking at a k path. Earlier we were looking at a k path that was colorful. Now we are looking at a k path whose first vertex is green, second vertex is red, and third vertex is blue. So, and I'll try to find a k path for every possible ordering of these colors. So if there was one colorful path in the graph, then I would get a colorful path for at least one of these orderings, right? And if I am not able to find a colorful path for any of these orderings, then there was no colorful path to start with, right? So we spent k factorial time, and in these k factorial time we enumerate all possible orderings of these colors, and then for every possible ordering that we have, we try to find out, is there a path in the graph that respects this ordering? So if I have the ordering green, red, blue, I am trying to find out, is there a path whose first vertex is green, second vertex is red, and the third vertex is blue, right? So basically we have reduced our problem to finding such a path which respects a particular ordering of these colors, and we have spent k factorial time. So whatever running time we incur to compute such a path that respects such an ordering, that ordering into k factorial time will give us, in that much time we'll be able to solve colorful k path problem, because we will solve this problem for every possible ordering. So k factorial orderings, and for each ordering whatever time we take to find a path that respects an ordering. So now what we have is, we have a colorful graph G, integer k, and we also have a fixed ordering for the colors of G. So basically we have a fixed ordering, or let's say we have a permutation of 1 to k. So k 1 to k were the colors, and we have a permutation of the colors. And what we are interested in, so let's say this is the input, and we are interested in finding a colorful path that respects this ordering that is given to you. Okay. So again, so now I'll not draw colors, I'll just write numbers. So suppose this was the graph, this was the input graph, these were the vertices that get color 1, these were the vertices that get color 2, 3, so on, k. And suppose the ordering that is given to me is, let's say 2, 3, okay, or let's for example say k was only 4. So let's say the ordering that is given to me is 2, 3, 4, 1. So the problem that we are trying to solve is there a path in this graph whose first vertex comes from this color class in 2, second vertex comes from this color class in 3, third vertex comes from its color class in 4, and the last vertex comes from the color class in 1. Right? That's the kind of path that we are looking for right now. So let's see if we can find such a path in the graph. So again, this was the original graph G, and I have fixed an ordering 2, 3, say 4, 1. Okay, I fixed this ordering, and we are looking for a path whose first vertex is from 2, second from 3, third from 4th, and the last one from first vertex. So again, because we are looking for such a path, so let us look at all the vertices which got color 2 in the graph. Let us look at all the vertices that got color 3, all the vertices that got color 4, and all the vertices that got color 1 in G. So we are looking for a path that starts from a vertex here, goes to a vertex here, and then to a vertex here, and then to a vertex here. How much can you find such a path in this graph now? So I have given you this graph. I've given you a set of vertices in the graph that are colored 2, set of vertices in the graph that are colored 3, set of vertices in the graph that are colored 4, and the set of vertices that are in the graph that are colored 1. And I'm asking you, is there a path from whose first vertex is from 2, second vertex is from 3, third vertex is from 4, and the last vertex is from 1. Right. So we just have to be careful when we are doing depth first search. For example, we should not use the back edges, right? So for example, if I'm doing a breadth first search starting from a vertex of 2, when I look at all its neighbors, I only need to look at the neighbors of 2 in 3, right? For example, I should not look at the neighbors of 2 inside 2 when we are doing it. So as they suggest do the following. We are interested in finding a path whose first vertex 2, second vertex from 3, and so on. They say do a depth first starting from the vertices of 2. Okay. So look at a vertex from 2, do a depth first, and they want to do a special kind of depth first where starting from the vertices of 2, they'll only look at the neighbors of 2 and 3. Okay. Then once they have visited all depth first, or okay, depth first, anything. So and then once you are at a vertex from 3, you'll only look at its neighbors in 4. And then once you are at a vertex in 4, you'll only look at its neighbors in 1. Okay. So this is the kind of depth first that they want to do. And how will you do such a depth first? Just look at the depth first algorithm. Just try to imitate the depth first algorithm at any point when you are looking at when you traverse a neighbor of 2. If the depth first asks, if the neighbor of 2 that the depth first asks you to traverse is not from 3, then you don't traverse that neighbor. In other words, what one could do is, like, instead of, he's using the depth first algorithm, but at every point you'll have to check something, right? So that you don't do anything crazy there. So instead of that, what if I do the following? I had been given this graph G, which had color classes 2, 3, 4 and 1. Okay. What if I do the following? I just remove all the edges that were incident between 2 vertices of 2. I remove all the edges that were incident between 2 vertices of 3, because I know that the kind of path that I am looking for will not use those edges. Similarly, I remove all the edges that were inside any color class. I just remove them because I actually want to do the same kind of depth first that he is suggesting, but I want to use the original depth first algorithm to do it. I mean, I don't want to check this at every point that whenever I am traversing a neighbor of 2, I should always traverse a neighbor of 3, and if that's not the case, I should do something. So what I do is I actually remove, if there were some edges inside this, I just remove them from the graph. If there were some edges inside this, I was remove them from the graph, and so on. So I make these graphs independent now in the graph, just so that I could do the depth first to get a path, such a path that has first vertex from 2, second from 3, and so on. Does this solve the problem? Now if I do depth first, will I always get a k path? Yeah. So like again, when I'm doing a depth first starting from 2, I'm in the depth first might there might be an edge from a vertex of 2 to a vertex of 4, and in the depth first starting from 2, I might directly jump to a vertex of 4. So the path that I'll get will have first vertex from 2 and second vertex from 4, but that's not the kind of paths that we are looking for, right? So for that also, what we can do is, we know anyway that the kind of path that we are looking for will never use this edge, right? So we can just remove these edges also. In fact, we can remove all the across edges as in edges that go from vertices labeled, colored with different colors. Like we'll remove all the edges that go across 2 different color classes, provided they are not adjacent in the ordering. So I'll not remove edges between 2 and 3, or 3 and 4, or 4 and 1, because those edges will be used could be used by the path that I'm looking for. But my path will never use, for example, these kind of edges or these kind of edges. Oh, 3, 1 I've already taken. 2, 1, yes. So it will not use this kind of edges. So what I do is, just to perform the kind of depth first that he was proposing, I just delete all these kind of edges in the graph. I know that if there was a k path, the kind of k path that I was looking for in the graph, that path will still be there in this graph, because that path was not using any of the edges that I just deleted. Now how does the graph look like? There is a set of vertices that are colored 2, all of which are independent. They have neighbors only into 3. All the vertices of 3 are independent. They have neighbors only into 4. All the vertices of 4 are independent. They have neighbors only into 1. Now let us do this depth first, starting from a vertex of 2. So depth first, once it is at a vertex 2, the only option it has is to go to a vertex of 3. Once it is at a vertex number 3, the only option it has is to go to 4, and from 4 the only option it has is to go to 1. So do the depth first. If in that depth first you get a path of length, for example in this case 4, you say that there is indeed a path that respects this ordering, right? Because with respect to this ordering, we did this cleaning procedure. So if the ordering given to me was 2, 3, 4, 1, the procedure that I did was remove all the edges inside 2, inside 3, inside 4, inside 1, and then remove all the edges from 2 to 4, 2 to 1, and 3 to 1. And after that, I did DFS and found a path. And if it returns, and if in the DFS tree I get a path of length 4, then I know that that corresponds to a path that respects this ordering, because I was doing the DFS starting from a vertex of 2. So what have we done? We wanted to solve the colorful k-path problem. For that, we said we are looking at a path which where all the vertices get different colors. To find such a path, we said let us the order in which the vertices of the colored path that we are looking for appears. So we are looking colored path. Let us guess in what orders do the colors appear in that path? So we did k factorial guesses. For each such guess, what was a guess? Guess just corresponded to a permutation of these colors. So for each such guess, we solved this problem. What is this problem? Given a colorful graph G, K and a fixed ordering of the colors, we tried to find, is there a colorful path that respects this ordering? Respects this ordering meaning the first vertex of this colorful path is colored with the first thing in the ordering, first color in the ordering, the second vertex of the colorful path is colored with the second vertex, second color in this ordering, and so on. And we solved this problem how? What did we do to solve this problem? We just did some pre-processing in the graph. I mean, what is this pre-processing? This is like deleting all the edges inside 2, 3, 4 and across edges, and we did that, and after that we ran DFS on this. Right? Given a fixed ordering, finding if there is a path respecting that fixed ordering, this portion can be solved in polynomial time, right? Because the first step is you have to delete unnecessary edges. That you can do. What you have to do to delete unnecessary edges, you just have to see if there are two edges of the same color, delete it. If there are two edges which get colors such that the two colors are not adjacent in the ordering, then you have to delete those edges also. So this is just some polynomial time procedure. And then after that run DFS, which is again a polynomial time algorithm. Linear, but let's say polynomial. So this problem can be solved in polynomial time, and hence the colorful k-path problem can be solved in this k factorial into polynomial time. So we have solved the colorful k-path problem in polynomial time. And what was the goal? Our goal was to actually solve the original k-path problem. Right? So, and now we have an algorithm with running time k factorial into polynomial in n for the colorful k-path problem. Using this algorithm, we want to design some f of k into polynomial in n algorithm for k-path. So what could one possibly do? I have given you an algorithm to solve colorful k-path. So now to solve the k-path problem, you can use this algorithm as a black box. Right, the colorful k-path problem as a black box. But how will you solve the k-path problem using the colorful k-path problem? So what is a k-path? You just want to find some path. In the colorful k-path, you want to find a colorful k-path, right? And moreover, if you want to use the colorful k-path problem, the input instance itself has to come with some ordering, some coloring on the vertices of the graph, right? What does it depend on? See, first of all, you have to tell me for what coloring should I do this? Even for the first thing to hold, whatever you said, that will hold for any coloring. So, for example, let's do the following. Let's arbitrarily color the vertices of the graph. So, now we are solving the k-path problem, okay? Okay. As of now, let us arbitrarily color the vertices of the k-path problem. And now this becomes an instance of the colorful k-path problem. As in, now I have a graph G, an integer k, and I also have a coloring on the vertices of the graph. And let us try to find a colorful k-path in this graph. If the algorithm says yes, then what do you know? So if the algorithm is actually able to find a colorful k-path in such a graph, then what can you say about this problem? So in this problem you wanted to say, is there a k-path in the graph or not? You find a colorful k-path, then is there a k-path in this graph? Yes. Yeah, because you just forget about the colors and that's a k-path. But if you are not able to find a colorful k-path, then can you say that there is no k-path in this graph? No. Why? And okay, of course, it's you can't say that. But why is this happening? Like, it's because the coloring that we chose might not have made the vertices of the k-path that was there in the original graph colorful. That's the reason that we are not able to find such a path. Like, if suppose I knew that the coloring is such that if there is a k-path, then this coloring will give distinct colors to the vertices of the k-path. Suppose I knew this from the kind of coloring that I have done, then will this problem occur? Then if this says no, can there be a k-path in the graph? No. So it all depends on the kind of coloring that we choose, right? So right now we just said, given a graph, arbitrarily color the vertices of the graph and find a colorful k-path. But now if I do the coloring in such a way such that, suppose as of now, it ensures that if there is a k-path in the original graph, it will become colorful in this ordering. Then I'm done, right? So this is the coloring from the vertex set of the graph to k colors. So there are some k power n colorings that a graph G can have on k colors, right? Every vertex can have k colors and there are n vertices. So the total number of vertices, the total number of colorings that such a graph can have are k power n. So the total number of choices for such a coloring could be k power n, okay? Let us uniformly at random pick one coloring from the set of k colorings of the graph and run the colorful k path problem on that coloring, okay? So it's not an arbitrary coloring, it's a coloring chosen uniformly at random from the set of all possible k colorings of the graph. So now that we have bring in probability, whatever we can say is, like, we can just say that something happens with probability. So suppose I started with such a random coloring. Again, if I find a colorful k path in the graph with this random coloring, what can I say about the k path in the original graph? It's still there, right? No matter what coloring is, if you have a colorful k path, that's still a path in the original graph. So this direction is always true no matter what this coloring is. It's random, arbitrary, no matter what this coloring is. If there's a colorful k path, you always have a k path. Now we have to argue the other direction. The other direction being, if there is a k path in the original graph, we want to say that then you will actually find a colorful k path in this graph. And so, and because this coloring is randomly chosen, we want to say that if there is a k path in the original graph, then with at least this much probability, I'll find a colorful k path in this graph, and that probability should be high enough. I mean, okay. So now what we are doing is, we are basically at this point of time, we are trying to design a randomized algorithm for this problem, whose running time will be some function of k into polynomial in n. Later, hopefully, I'll just tell you how one can make this, one can make this algorithm deterministic, as in how one can prevent this randomized step. But I'll not be able to give you the proof of that theorem, but I'll tell you a theorem that that's a very standard tool that people use to de-randomize such sort of algorithms. So I'll just tell you that. Hopefully, once I tell you the theorem, it will be clear why this can be used to de-randomize it. But as of now, we are trying to design a randomized algorithm for this problem, by which I mean the algorithm's running time is always f of k into polynomial in n. So basically, it's the Monte Carlo algorithm that Anita was talking about yesterday. So the running time is always f of k into polynomial in n, but this algorithm might output wrong answers sometimes. So for example, there might be a k path in the original graph, but this algorithm might say no, okay? But it will say no but ideally I want to say that whenever it says, the probability when there is a k path and it says no is very less. That's the kind of that's the kind of algorithm that I want to design, right? So what do we want to prove? So we chose a coloring uniformly at random. Basically, we want to compute what is the probability that if there was a k path in G, then this coloring makes this k path colorful. So if we can compute this probability, then this is the probability with which our algorithm is always correct. So if it was yes, then with probability at least the same as the probability with which C colors the vertices of this k path colorful, with at least this much probability, the algorithm will always output the correct answer.